Thank you also to Tom for introducing some of the terminology on draconitics, because we were talking a little bit about those here as well. So yes, I'm going to be talking about the Tiger combination, and it's a long time coming actually, since introduction of Tiger, quite a long time ago, and sort of the first combination didn't happen really, and then Repro2 came, and finally there's a combination. But all of this work was done by my colleague Dr. Yu Now at the University of Luxembourg, so he's the first author. And of course, I would like to acknowledge at this point also the contribution by the authors or co-authors from all the contributing solutions analysis centers. I will start off generally with some background. Then I will talk a little bit about the Tiger combination itself, and then about the internal and external evaluations we have carried out. And the external evaluations I call a comparison to ITRF 2014, to the JPL and NGL solutions. So NGL is, I have termed it the Nevada Geodetic Laboratory rather than the UNR solution as in the previous talk. And also we have carried out some very quick comparison to absolute gravity vertical rates. And then we actually look at what is the impact on sea level change estimates before we come to the conclusions. The issue is, many of you are aware, but the issue is that means sea level these days is still measured by tide gauges, not just by satellite altimetry from space, but tide gauges have an important role. And different parts of the Earth show different vertical land motions due to natural processes, due to human-induced processes. On the top list, we have the tide gauge record of Stockholm. It's GIA. You are aware of that. And this is, let's say, a more easier process to model. It's in a way linear. But when we go into the middle of the graph on the left, we see that, for example, some areas have very non-linear motions. Also, for example, the high altitudes or latitudes, the polar regions like the Arctic or Antarctica, where we see lots of non-linear motion. And this is, of course, an issue. And that is also a reason why in the early days, GPS was seen as a potential tool to measure those vertical land motions directly at the site. So if I take you back in time a little bit, the first idea of this came in an IAPSO committee meeting that was summarized in the first Carter report in 1989. And there it was suggested that GPS, gravity measurements, I mean, even the use of VLBI and SLR was considered for measuring the vertical land motions. After that, there was a first attempt of doing so in the UK, and it was published in JRL in '93 by Ashkenazi et al., using episodic GPS campaigns. So we now know as well that, of course, episodic GPS measurements are not ideal for the long-term monitoring, especially of the vertical component. Then was the second IAPSO committee meeting, and there was the IGS PSMSL meeting. In fact, that was, I believe, the first IGS meeting at Pasadena in '97. And again, then it was suggested, in fact, continuous GPS might be the better option of doing the vertical motion moving or monitoring. And after that, really, the ball got rolling, and lots of studies came about in the UK, in the US, and all around the world. But in the end, it turned out not to be as straightforward as initially thought. And as Tom Herring pointed out, the scale plays an important role here. So for sea level studies, of course, the vertical component is the one and only that is of primary concern. And really, it's the geocenter and the scale, the origin, that are the two parameters in the reference frame that play an important role here. And in various meetings in the noughties in 2006 and later published in a book in 2010, a report by a group of people from here was that we needed a frame stability of 0.1 millimeters per year and a scale stability of 0.01 parts per billion per year. And then this meant an improvement in our reference frame by the order of magnitude. What we see on the right is just an illustration of actually what a scale change and change in the origin actually does. And below is a very rough demonstration of what, for example, a rate in the Z component would do to your vertical rate, as we have seen at the switch from ITRF 2000 to 2005. That, for example, the equator would see very little effect, but, for example, the polar regions, which are so important, not just for sea level monitoring, but for these days for the monitoring of the vertical lift because of ice mass loss, these are the most affected one. In a different way, a report by the National Research Council in the US included this figure, which puts the application to sea level really as the most challenging application for GNSS. Not only do we need millimeter precision and accuracy in our results, we also need those over many decades. And in a way, I like to say that out of the work of the analysis centers involved in TIGER in the early days, it was also that those are the ones who sort of instigated the first reprocessing campaign by the IGS. And of course, now we understand that a regular reprocessing is a necessity, but it wasn't always that day. I believe people also in the early noughties saying, well, there was not much to be invented in post-processing GPS anymore. And soon after that, actually, the antenna phase centers came up on the radar. So when we turn to TIGER now, so of course, the main objectives and goals of TIGER are to produce solutions that can be used by the sea level community. And those solutions contain positions, a combined solution, and then vertical velocities. They also promote the establishment of GPS or GNSS stations in the southern hemisphere. At the bottom right, we have a figure showing the inequality in the number of stations between the southern hemisphere and the northern hemisphere. It's not as bad as this anymore. This figure is a few years old, but it is still pretty dire. And of course, it won't change because we're just missing the land in the southern hemisphere. But also one of the target really is to promote the establishment of the local ties between the GPS antenna and the tire gauge benchmark. And even while I'm talking about GPS today, within the community, it's still very, very difficult to get these connections between the tire gauge benchmarks and the GNSS antenna. And finally, TIGER, of course, holds very, very important links. One is to GGOS, especially theme 3, sea level rise and variability. And the goal there really is much in line with the goal for TIGER, but more in the identification and the requirements for understanding or for improving our understanding of global and regional sea level rise. And therefore, GGOS really tries to establish more links with various organizations involved. And of course, in the end, TIGER is also supported by the UNESCO, the IOC, the International Oceanographic Committee, by GLOS, the Global Observing Sea Level Service, and by GCOS, the Global Climate Observing System. Okay, this brings us really to what has been happening in TIGER. In TIGER, we currently have 5 analysis centers, TACs, TACs, whereby the first one, AUT, joined us in October 2016, so that's a very recent attribute. Otherwise, we include the BLT, the British Isles Continuous GNSS Facility, and University of Luxembourg, a combined effort for the processing, then DGFI, which is of course now being integrated into the Technical University Munich, GFZ in Germany, and ULR at the University of La Rochelle. And with the contributing authors being listed on the right-hand side. If you look at this, you would think that we have a very Bernese dominated solution that I'm going to talk about, but it's not that straightforward just yet. One of the conclusions from the earlier days was that the Tiger networks had to be much more homogenized than they were in the noughties. And one of the recommendations was in 2010 that all networks had to include the IGS core network plus its spare sites, so that combination would be possible. And here we see the different networks processed by the different analysis centers. So we're talking roughly between 400 and 800 stations processed by any one of them. The data, of course, is archived at the University of La Rochelle at zonel.org. And also, I think there's a backup at CDDIS. When I talk about the Tiger combination, for me, it's a little bit of a story of delays and patience. I mean, I've indicated it's been going on for a long time, and there's a lot of pressure that this is finally released. After initially, in 2009, it was sort of recognized that there was not going to be a combination of these. It made no sense really to make a combination for the Tiger analysis, because if you look at the right-hand side of the networks were completely heterogeneous. There was partly no overlap. There was no way of combining that. So in 2011, the Tiger took the decision to do a parallel processing to the IGS Repro2. And as some of the TACs, or the tags, required the reprocessed products, they had to wait until Repro2 was completed. Then we had issues with software bugs that required a second reprocessing by some of the analysis centers. And there were numerous other issues and external factors that caused delays at no end. We, in the meantime, produced some preliminary solutions where we included those tag solutions that were available and additional IGS solutions just to stabilize, in a way, our combination. But then we took the decision in late 2016 that, okay, we are now sticking to the Tiger solutions and take them forward. But in the end, after much waiting, we still only ended up with 3 solutions ready for combination. When we do the combination, that was done at the University of Luxembourg. Basically, we wanted to produce an IGS type product, a combined solution. And we're doing a daily combination of SINEX files contributed by the TACs. Of course, important are the modeling in this of the station position time series, in particularly offsets and nonlinear motions associated with earthquakes. So there's a lot of work that has gone into that before we do the long-term stacking. And initially, we got the Tanya software from Newcastle, but also CATREF and GlobK. We did several tests, but for us, as a small group, it was in the end too much to do multiple solutions, and we had to focus on one, and we went with CATREF software to do the combination. Then we spent some time, actually, early last year, in introducing the postseismic deformation modeling into our version of CATREF, which was then, of course, released later on as well in the official version. But we sort of introduced exponential log models for calculating these nonlinear motions after an earthquake, so that you have them correctly handled in the stacking. And we found that about 119 stations were affected by that, and which totals to about 11% of all the stations. And just to show you how this works out, for example, following the ITRF 2014 approach, we have a station here, ANTC, Los Angeles in Chile, and P104, Oga in Japan, both affected by earthquakes in the horizontal components, but also in the vertical component. And of course, the effect of introducing the nonlinear motions on the horizontal is enormous, but there is always a significant improvement also in the up component. When we're talking about sea level, it's not just the application to sea level, it's not just the GPS time series that has an offset. If we want to apply this whole vertical land motion thing to the sea level change, of course, we also need to apply it to the sea level time series themselves. And we see that, for example, here we have the Tohoku 2011 earthquake, and here with a set of Tiger GPS stations from Japan, and you can clearly see how all of them basically changed their signature, but also at the same time we have a change in a sea level record. So with the application in mind, one needs to keep also the sea level record in mind. I mentioned earlier that we managed to get 3 TAC solutions to combine for the first Tiger combination. So we used 6,936 SINEX solutions, daily positions between the 1st of January 95, 1st of January 2014, and in total over the time span it was 1,087 stations. Of course, at any one time, fewer stations. What we see below there is a figure of how often each station was included in one solution, because strictly speaking, in the IGS, you don't provide a solution if not at least 3 processing centers analyze the station. And that means that the green ones and the red ones in our solution would drop out. But we have kept them in, and the red ones are strictly no combination, of course, if only one analysis center produces a solution for them. But this is also a point where I would like to say that the Tiger Analysis Center have done a great job in actually including these extra stations, because today within the IGS everybody is used to having log files that are working pretty well, station information for each software that is partly or mostly correct. But when you bring in when we brought in the Tiger stations initially, there were lots of stations where the log files didn't work, where the data didn't work. And not only us, I believe also the other analysis centers spent long and much time on the fact of actually bringing the information, the station information of these extra stations up to scratch to actually process. And even then, during the stacking process, I know from Adishu that it took many, many hours to find the one non-performing station on a day that, for whatever reason, wasn't liked by the solution. On the right-hand side, we see some histograms on the statistics of the data length at the top, and then at the bottom also of the number of data points in the time series themselves, which sort of helps to overcome the issue of how to explain the gaps or to deal with gaps. So from the combination, of course, we then have our time series. And what we see here, we've taken 2 examples, WSRT and VAS, both in Europe, one in the Netherlands, and VAS, I think, in Finland. And at the top, we see the individual contribution TAC solutions, and at the bottom, we see the Tiger combination. And also, as Tom has pointed out, and as is the day-to-day business within the IGS routine analysis, if you bring in the individual solution, your combined solution tends to actually has an RMS value that is reduced compared to the individual ones, which is one of the reasons why we do this combination. We also gain an idea of the quality of the individual solutions. So this is the case here. We see that as well. We might see that from these figures that the GFZ solution might have been the one with the least noise initially, and the BLT solution maybe the largest noise from those 3 solutions. I like to point out that the GFZ solution here, with being based on the EPOS software, is a PPP solution, whereas BLT and ULR are both double difference, one with Bernice and one with Gamut. So we got the main scientific softwares here represented at an equal playing field. When we look at the daily RMS overall stations for the combined solutions, we see the plots that we know from the IGS as well. Of the RMS of the height component in green and blue, and in red the contributions from BLT, GFZ and ULR, and in pink the combined combination. And clearly the early days until about 2004, it was rather noisy, but then from 2004 onwards, there was a very nice agreement between the two, maybe with the BLT solution being slightly noisier. But we're having a level of overall of about 5 to, let's say, 7, 8 millimeters RMS in the vertical component. Looking at the power spectra of these solutions, the individuals and the combined, at the top I have the east and the north component, and at the bottom we have the up component. We see that we see the picture that we have seen quite often recently. We have the annual and semi-annual signal, but then we also have the peaks at the draconitics and the harmonics of them. And as Tom pointed out, they are related to the GPS or the constellation that goes into here. I'd like to point out here a paper by Abraha et al. In 2016, December, which looks at this in particular based on stuff that has been done by Jim Ray and Jake Griffiths in the past. When we look at the Helmut transformation or the translation parameters, so what we've done here is we've got the translation parameters between the combined solution from Tiger and the IGB08 solution. We are still in ITRF 2008, and we see the TY, TX, and TZ components. The TZ components is rather noisy, and I believe, well, this is due to the ULR solution that comes in with that noise level. This is also something that is known from the combination within the IGS, Repro2. Paul Rebichung has noted that before, and it's to do with the way the ULR define the daily global networks. On the right-hand side, we see the power spectra. Again, we see the strong annual and semi-annual components, but then interestingly, for the TZ translation, we have a very prominent 4th and 6th harmonic. And at the moment, I don't know where they come from, but that's something we will have a look at. When we look at the terrestrial scale, the scale as one of the key parameters, we have here the scale estimate between the Tiger solution based on this network of 70 core stations to IGB08. So we see the typical picture again of the very large variations in the early days, and then reducing this variation with these highly annual signals in there. But we looked also at where these variations come from, and when we fit the model, which you see in the table below, you see a bias of minus 1.8 millimeters and a trend of 0.02 millimeters per year, annual and semi-annual signal. We've taken the approach by Paul Rebichung to actually take those values that for a loading model that have been prepared to ECMWF and GLDAS and ECHO2, and in fact the values compare fairly well with the values we have obtained. On the top right, we see the periodogram or the power spectra again of the scale parameter, where we also have this very strong yearly component, the semi-annual component, and also some peaks in the harmonics. When we then step to the actual vertical land motion estimates, here we have on the left-hand side, we have the Tiger combination, and on the right-hand side, we have the vertical velocity field from ITRF 2014. You will see many similar velocity rates, but also I like to point out there are definitely some stations which are different. For example, here in Central Asia, which is a much larger rate in ITRF 2014 than what we have. This is potentially related to the fact the way we have actually come up with the lists of discontinuities in our files. We have started off with initially with the discontinuity file of ITRF 2008, then replaced that with ITRF 2014, and then to those we've added the discontinuities that we have obtained from a visual inspection of the time series. So a lot of work has gone into that, and we are certainly have more offsets in the end in our modeled more offsets than was modeled there. And of course, when you do this, you tend to, the more offsets you include in a time series, the lower your velocity will be, the closer it will be to zero. So we will have to look at this, but if there is an undetected offset in a different solution and we have an extra one, it might take away some of the magnitude. We have also compared to other GPS solutions, and in particular of JPL and NGL, compared also, of course, with ITRF 2014. And here we see the histograms of those. And in each case, it was about we see here about 300 to 400 stations. We weren't able to take exactly the same amount of stations, as not all the stations are being processed by the different analysis centers. But we see that, for example, for ITRF, we have a very, very small RMS, a good agreement, but we have a slightly larger bias than for the other two. And we can say that about 57% of all velocity differences are less than 0.5 millimeters per year. And these percentages are slightly lower for the JPL and NGL solutions. So don't forget that the JPL and NGL are individual solution. ITRF is also a combination. Tiger is a combination. And the other thing that is in here, hidden in here, is actually ITRF is ITRF 2014. The Tiger combination plus JPL and NGL are ITRF 2008 solutions. If we look at the time series themselves, for WSRT between the Tiger combination, JPL and NGL solutions, again, we see lots of similarities, and because the Tiger solution is a combination, I would say that I would like to argue that the RMS is obviously slightly lower than for the two individual solutions. But overall, we seem to look at very, very small differences. Very quickly, we have also done a first look at comparing the vertical velocities from the Tiger combination with absolute gravity. Those who know me know that I have done this in the past. And the argument for that is absolute gravity is a measurement technique that is independent of the reference frame. It's an absolute measurement. It comes with its own problems. It's very much affected by hydrology, but it is not affected by biases in the reference frame. And that's why I like to always cross-check the vertical rates that we get. And if we look at the two plots here, on the left we have a station in the UK, Newlyn, and on the right-hand side we have Ny-Ålesund in Spitsbergen, Norway. And for the left, we had to cut the GPS time series because in the UK, unfortunately, the absolute gravity measurements in Newlyn stopped in 2007, 2008. So we had to cut our nice long Tiger time series to a shorter one, estimate the velocity, and compare that. For the Ny-Ålesund, it's possible because the absolute gravity measurements are still ongoing. But for Ny-Ålesund, this is just one of the published values. There are other published values which are actually higher as well. So it's not a complete picture here, but we can see that there is agreement, especially, of course, if you take the 1 sigma uncertainties into account. For Newlyn, the different solutions agree to roughly within a millimeter per year. In fact, some are actually, the actual value is less than half a millimeter per year different. For Spitsbergen, the differences are similar. But as I said, I think even though the uncertainty for the absolute gravity measurements as taken from this publication, I think it's rather small, because depending on the conversion factor, how you change the change in gravity into a change in millimeters per year into a height change, you're shifting your gravity there. Coming now to the application to sea level, This is a figure that similar to Whippleman et al. 2006, basically looking at mean sea level records, then correcting them with the GIA models, which was done initially, and now with GPS corrections. I can go here quickly because, in fact, this shows to a degree much more what it actually does. On the left-hand side, we have the GIA, and on the right-hand side, we have the GPS-derived vertical velocities. In blue, we have the mean sea level trends uncorrected, and in red, we have them corrected with vertical land motions. And you can see how on the right-hand side, individually, large moving stations can be corrected much better using the measurements actually at site than with GIA. Putting this together, one can take the 29 stations as proposed by Douglas in 2001, 29 tide gauge stations, add them together, correct them for the land motion. I'm going through here and come up with this table here. Initially, the variation, the scatter in the mean sea level trends is about 2.08 millimeters per year. If you correct for land motions with GIA models, you have 1.26 or 1.3. But if you actually apply GNSS-derived vertical land motion estimates, you're coming down to 0.6 millimeters per year. That brings me to my conclusions. I have basically presented you the first TIGA combination. We call it Release 1. It is currently includes 3 contributing analysis centers, but we are awaiting the contribution from DGF and AUT. The solution, the individual contributions have high consistency, and they perform fairly equivalently. Maybe the solution from GFZ is the least noisy one for the stations we have looked in particularly. We have also carried out some external evaluations, which are very, very important to come and look at those. With ITRF 2014, other GPS solutions, and absolute gravity. Certainly, from a personal perspective, I like to expand on the comparison with absolute gravimetry again. Expand this to more locations around the world. And it's important to bear in mind as the external evaluation of this, as has been carried out, for example, by Collier et al. In 2016 in the past, how to analyze the reference frame and the products. We need to look at that. And with that, I'd like to end up say thank you very much.